In the first part of this video, we are going to discuss about tone modulation for narrowband FM. Next, using a single tone message signal, we have a MATLAB implementation. So for this MATLAB implementation, the code is given in the description of this video.
So assuming that we have a tone modulation in narrowband FM, and by single tone message signal we mean that we are concentrating only on the cos omega mt, where omega m is the radians per second or the angular frequency of the message signal, and am is the amplitude. So this is a message signal that we have. So if this is the message signal m of t, so from here we can determine the instantaneous angular frequency omega I of t, which is equal to the carrier frequency omega c plus the sensitivity parameter kf times m of t. Next, if we plug in the value of m of t, so we would have we may have another equality over here, which can be omega c plus kf am cos omega ct. Right. So this whole thing kf am we have referred it as delta omega. We have omega c plus delta omega cos omega mt, where delta omega or delta f is equal to delta omega over 2 pi. So what is this? This is basically the maximum frequency deviation. So what does it identify? It identifies that by what degree would we change the instantaneous frequency, right? So there are some very key factors which are involved here. First and foremost, you would see that delta omega is directly proportional to kf. This is coming from here. Delta omega is directly proportional to kf and am. So whenever this would change, then your delta omega would change. And when your delta omega would change, it would have an effect on the omega c in terms of addition or deletion depending on the message signal. Another important thing is that delta omega is independent of, let me write here, delta omega is independent of the message frequency omega m. So omega m does not play any role in defining delta omega, right, in the deviation in frequency. So from here, since we have the instantaneous angular frequency omega I of t, if you take the integration of it, omega I of t, if you take the integration of it, you would get the generic phase. And for that, we have an integration of 0 to t omega I of lambda d lambda, where the limit is from 0 to t and we are assuming initial condition. So if you plug this over here in this integral, so we would have omega ct plus beta sine omega mt. So where is this coming from? We know that if we take the integral of cos omega mt, so that would be equal to 1 over omega m sine omega mt. So that would be coming out of the integral. But at the same time, we also have delta omega, which is here, right? So delta omega by omega m is beta. And beta in FM is similar to the symbol that we used in AM, which was mu. That is the modulation index. So this beta is the modulation index. So when we are discussing about narrowband FM, so this value of beta is usually kept small. So it is less than 0.3. Modulation index beta is delta omega by omega m, or in frequency delta F by Fm. Remember 2 pi here would cancel with this 2 pi, so this is our modulation index, and it should be less than 0.3. With this, we can plug this argument inside a cos function. So our generic FM modulated signal is GFM of t is AC cos omega ct plus beta sine omega mt. Previously also I discussed that if we have a single tone signal, so if we have a single tone signal, this is a single tone signal. So this is a cos function. So if we integrate it, we would have a sine function. So from cos we would get sine, but we would also get 1 over omega m. So we would scale this factor over here. So that is basically the role of this integral. Right. So we have AC cos omega ct plus beta sine omega mt. Now what we do next is we expand this. Note that this is simply cos A plus B, which is equivalent to cos A cos B minus sine A sine B. This is a trigonometric identity. So from this trigonometric identity, what we can have is we have AC, which will be coming here. It's a coefficient, constant coefficient. So we would have cos omega ct, then cos of beta sine omega mt, cos beta sine omega mt, minus again the coefficient AC, then sine omega ct, and then sine beta sine omega mt, sine beta sine omega mt. These are very, very interesting aspects. So we can basically simplify this expression considerably. Note that the value of beta is quite small. It's less than 0.3. And similarly, we know that the sine function is oscillating between plus 1 and minus 1. So the absolute value of it is also less than plus minus 1. So overall, this whole argument of cos function, that is cos beta, which is 0.3 times plus or minus 1, since this is an even function, if it is plus 1 or minus 1, eventually we would have what you call cos of a positive argument. Right? So either way, we can say since the cos function have this shape, so this whole argument would be very, very small. If it is small, we will be very near to the origin, and at the origin we know that cos of 0 is equal to 1. So this whole thing can be approximated to 1, right? That's why in this expression we have AC cos omega ct, whereas we have normalized the second function. You can note that this is an approximation, so we can change the equality to an approximation here. A thing that we have done previously when we expanded the Taylor series and cancelled the higher order terms. Right. Similarly, this function sine beta sine omega mt. No, again, beta is having a smaller value for the narrowband FM, so less than 0.3, and similarly sine omega mt. So you can observe that in the sine function, the behavior is something like this. So if x-axis is simply beta sine omega mt, and this is sine of beta, then again sine of omega mt. So if the value of this whole argument is small, since beta is small, sine omega m is small. For smaller values, you would be near the origin. And if you are near the origin, there is a linear behavior around the origin, kind of a linear behavior. And then we have some increased slope as we move onward, and then it oscillates back. But in this region, it is almost linear. So if it is linear, whatever is on the x-axis, that would eventually be translated onto the y-axis. And for that purpose, we can say that the sine beta sine omega mt is approximately equal to beta sine omega mt, right? So we got rid of this sine function, and we just got the argument itself from this property. So this whole thing would translate to this simply sine omega mt, and the value of beta we have included as a coefficient. Now this is a simple straightforward expression, so it would just relate back to the low expression. But we can simplify this expression furthermore, such that we use a property sine x sine y. So this is equivalent to 1 by 2 cos x minus y minus cos x plus y. Since we have a minus here and we have a minus here, this minus and this minus would eventually cancel out, and you would have cos of x plus y multiplied by 1 by 2. So the coefficient AC beta by 2 cos omega c plus omega m of t from here, x and y. Omega c plus omega m of t. And then this plus would become minus because of this negative sign. It would become minus AC beta by 2 cos omega c minus omega mt. Not exact, it's an approximate expression, but nevertheless it's an analytical expression. Now this is a time when we compare our narrowband FM with AM, and there are striking similarities between the two. The whole of this derivation that we have done so far, I have just recreated it or reproduced it over here in this expression. That is AC cos omega ct plus AC beta by 2 cos omega c plus omega mt minus AC into beta by 2 cos omega c minus omega m into t. Now, if you compare this with our amplitude modulation, what we have is we have in amplitude modulation, first of all, this is an approximation, this is an equality, but anyways, so we have AC cos omega ct, so no change in the carrier. So this is as it is. And then we have AC beta by 2 over beta is the modulation index in FM, and mu is the modulation index in AM. This is AC mu by 2 cos omega c plus omega mt. So again, this is similar, but we have a change of sign, minus and plus, minus in FM and plus in AM. AC beta by 2 and then the lower sideband, and plus the lower sideband. So the major difference is we have a change in the sign of lower sideband. Here we have the upper sideband for both of them, and this is the lower sideband. So if we plot the line spectrum in terms of omega, so we would have omega c, which has an amplitude of AC, and then we would have omega c plus omega m. This would have an amplitude of AC beta by 2. Okay, so let me just rephrase this. We cannot say this is an amplitude. We say that the area is actually equal to AC, not the amplitude. The amplitude is infinite and the width is almost zero because this is a representation of a direct delta function. So we would say the area is equivalent to AC, or simply we can say the strength is equivalent to AC. And over here the strength is equivalent to AC beta by 2. And for the lower side band we would have a negative sign at omega c minus omega m. This is minus AC beta by 2. So this is our line spectrum. Whereas in AM we simply had the line spectrum like that for these values. Another important consideration is that we're having a value of beta which is less than 1.3 or less, and then we are further dividing the whole thing by 2, so that's why the strength of upper sideband and the lower sideband would be less. Okay, so an important point, basically the theme of the whole discussion was about the bandwidth. So the bandwidth we have similar on the negative side. So, but the bandwidth is basically concerned to the positive frequencies. So the bandwidth over here is starting from this frequency omega c minus omega m lower sideband to the upper sideband, and hence this is equivalent to so 2 omega m. This is also 2 omega m. So there is no change. But remember, this is coming from the assumption on beta value. If we relax the assumption on beta, the bandwidth of FM would in fact be greater than that of what you call AM. I just want to reflect again on these two equations in terms of phasor diagram. So coming back to the AM first before moving to FM, our reference phasor is the carrier signal. So that is basically represented by this vector. And then for the upper sideband, we have a deviation of a phasor towards the upper side, and then for the lower sideband, which is this one, we have the deviation towards the lower side. But the sum of the two, the resultant, would basically add like this, and eventually our new signal would have that the carrier for the new signal would have this amplitude. Previously, the amplitude was vanishing at here, but right now it would vanish at here. On the other side, that upper sideband is unchanged. So whatever was here, we still have over here. But the lower sideband is reversed. So basically, this thing got reversed, and now you got this at the lower sideband. And the resultant of the two is basically making a right angle with the carrier. So the main point, what we are discussing here is that in the resultant, there is a small change in amplitude as compared to a large change in AM. So even though there are some striking similarities, there are also fundamental differences. That amplitude is not conveying information, it's the frequency which is conveying information. Whereas in AM, it is the amplitude which is basically conveying the information. Next, for the same single tone modulation, there's a small setup. I have set the time t, which is starting at -1 and then incrementing it by the value of 0.01 and terminating at 1. I set the frequency, carrier frequency at 5 Hz and the message signal at 2 Hz. The message signal is a single tone which is crossed to FM pi t, and then I have some parameters of FM modulation starting with the sensitivity parameter KF, which is 1e. Let me just start with smaller value, -1 times pi, so that the overall value is small. Delta function is the absolute value of kf maximum of the message signal. This we have discussed previously over here. So the delta function is the maximum value. So am is the maximum value. Cos function is oscillating between +1 and -1. So when the cos function is +1, the am would be maximum, whatever it is. So this whole thing is giving us the maximum deviation. So that we have expressed as a delta function, delta f, absolute value of kf, maximum of the message. And then we have integrated, remember we integrate the message signal. So once we integrate this cos, we get sine, as expressed here, so cos and sine. And then we FM modulate it, cos 2 fc pi t plus m. Then this is basically coming from, this is omega c plus kf a of t, or the integration of the message signal, right? And for the frequency response, for the plots, I have used a simple fast Fourier transform. So if we run this code, so this is our message signal, unmodulated baseband signal, baseband message, and this is frequency modulated signal in time domain. So these are two plots in the time domain. An important parameter over here is that we have, since it's a narrow band, we have set the sensitivity parameter to be very small, and since it is small, the actual deviation from the carrier frequency is not very prevalent, so we cannot really observe it directly. So even if it is at plus at a higher amplitude, the change in frequency, at least from the naked eye, is not very visible. The main point is that we have to observe whether this is following a narrow band or not. So if for the message signal, if we plot the frequency response, we observe that the main lobe in the frequency is around 250 hertz. So it is around 250 hertz. But once we modulate it, it would be at 500 hertz. So the frequency is almost doubled. This is in parallel with or similar to that of AM, where the frequency doubled for an AM signal. Remember, this function over here is AM with large carrier, upper side band, lower side band plus the carrier. So this is the generic AM. Next, if we set this kf to a high value, +1, then eventually we will have the message signal, and this is a frequency modulated signal. No, the differences are quite evident. You can observe that whenever the message signal is having a high amplitude, so the modulated signal would have more oscillations. So when it is at a lower amplitude, it would have actually very few oscillations. We plot the spectrum of this signal. So that is, as before, the main lobe is at around 250 hertz. But for the frequency modulated signal, the spectrum would be quite quite a lot. It would be much higher than 2 times the bandwidth of the message signal. Thank you very much.